right. Hopefully, unsurprisingly, the warm-up question today is a Kruskal's. So, use Kruskal's algorithm to find the minimum spanning tree of this graph here. Go ahead and take the next, let's say, 3 minutes, and then we'll talk about it as a group. I'm gonna see how the poll everywhere is going. I don't do that as often as I should. Let's see that. Okay, how are we looking? It looks like at least 60-ish people have finished. It looks like our most popular answer is 39. So let's take a look at this. So we're running Kruskal's. And remember that the way that we do Kruskal's, I put the pseudocode on here for you because you're going to have to write it in P4. But the way that we do Kruskal's is we take all of the different edges, we sort them by weight, we start with the smallest weighted edge, and we ask ourselves, does including this edge in the MST connect two previously disconnected vertices? So, what is the value, what is the weight of the smallest edge? I know there's two answers, but what's the weight of the smallest edge in this context? Yeah, 5. Now, there happen to be two 5s. If I was going to give you this, I would probably do unique edge weight so that we didn't have to break ties. It doesn't matter in what order you examine them. So let's start by examining, I think I did the animations this way. Let's examine this edge between A and D. Does adding that edge connect two previously unconnected vertices? Yes or no? Yes. Guess what? The answer to that question will always be yes. You're always going to add the smallest edge into the MST using Kruskal's. Which does make sense. We're trying to minimize the total edge weight. So we're going to include that edge. Yes. Okay. So now part of the reason the answer to that is always yes is because, remember, we sort of initialize all of the vertices to be considered disconnected from one another. And now we're sort of like, if it helps, you can kind of think of, we sort of are like lifting up on top of the graph, and we're thinking of an overlay over the graph. So we're sort of like finding a new subset of the edges, the MST, that is going to now connect all the vertices. So now, if that little islands analogy works for you, we previously had how many? Let's see, 1, 2, 3, 4, 5, 6, 7. We previously had 7 totally disconnected islands. Since we have combined, we've unioned A and D together, we now have 6. We have the one that's the connection of A and D, and then B, C, E, F, and G all on their own, lonesome. So now we're going to rinse and repeat. We're going to look at the other edge with the weight of 5. That's the one between C and E. Does that increase the connectivity of our MST? Yes or no? Yes. Again, remember our pattern with cruscals? We're probably going to say yes a lot in the beginning for those small weighted edges because there's not a lot of connectivity. Okay. The next edge, there is one edge with a value of 6. It connects D and F. Thumbs up, do we include that one? Does it extend connectivity? Thumbs down, it doesn't. The thumbs ups have it. It's going to now amoeba consume. I don't know. I'm like, ask the TAs. I'm like, I need as many analogies as I can come up with. But we are now going to extend the blob that was A and D to now include F. So in our total number of islands, we've got this sort of like 3-part island, we've got this 2-part island, and then we've got B and G just hanging out by themselves. Okay, the next edges are the ones that are weighted 7. There's 2 of them. Like I said, it doesn't really matter which one you do first. I think I considered the A and B one first in my animations. So does adding the edge weight 7 that connects A and B, does that increase connectivity or no? Yes, agreed. Also, if you've noticed now, every time we've said yes, it's because that edge is touching a vertex that was previously not touched so far in our comparison. So we're like, great, B, welcome to the biggest of the amoebas currently on the Petri dish. I don't know. Now let's look at the other 7 that connects B and E. What do we think about that one? Thumbs up, do we include it? Does it expand the connectivity? Thumbs down, we don't. This one's a little harder because it's sort of connecting now 2 blobs. But we can't finish with 2 blobs. We must have 1 blob eventually. So yes, I agree with the thumbs ups. This one also does include. So it took the blob that was previously C and E by itself, added that bridge, and now technically C, E, B, A, D, and F are all connected. Not necessarily in the fastest way to walk between any of those, but just in some way. They can all access the electrical grid. So there's really only 1 vertex left. And I'm just going to keep going until that vertex is now officially included in this blob. Thus, the blob includes all of the vertices. But I'm going to keep going in order. So the next edge has a weight of 8. There's 2 of them. There's one between B and C. Do we want to include the edge between B and C of 8? Thumbs up for yes, thumbs down for no. I love it. Love the head shaking. I agree. B and C are already connected, albeit sort of like walkabout because you got to go B to E to C. But that's fine. I don't care about how closely they're connected, how directly they're connected. So that 8 we do not include in the MST because it would cause what we call a cycle. And we can't have cycles in the MST. Let's look at that second 8. That second 8 connects E and F. Thumbs up, do we include it? Thumbs down, we don't include it. I agree. This feels very Roman somehow. The gladiators don't make it. I agree. We don't need that edge weight because E and F were already connected in the same blob. Because technically they were connected by going from E to B to A to D to F. But again, not about directness, Just some path exists in our MST. So the second 8 would have created a cycle as well. The next edges in our sorted edges order are the ones with 9. Let's start with the edge between D and B. Thumbs up, we include it. Thumbs down, we don't include it. Yes. Send it to the lions. Oh, great. I didn't do there it is. Okay. Pretend I swapped the order of those animations. Yes, the edge between B and D would create a cycle. B and D were already connected. They were already in the same blob. But because I couldn't remember the order of my animations, the other 9 connects E and F. And so far, F hasn't been connected to anything. So we are going to include it. So all of the green lines, I apologize for my colorblind folks, all of the green lines are the MSTs. The red lines are ones that we encountered and we decided we don't need. We could continue this algorithm, but we know from here on out, since every vertex is now officially connected, we don't need to keep looping. So we don't even need to look at that edge with a weight of 11 or with a weight of 15. Questions on the Kruskal's algorithm? I'm pretty sure this is one of your exercise problems, so hopefully you feel confident to answer that one. Okay, cool. All right, announcements. Okay, I finally got my stuff together and wrote out all the things. So EX4, I believe, was due yesterday. Yes, thank you. EX5 is officially out. It's your graphs exercise. There's a run of Dijkstra's on there. There's a run of Kruskal's on there. There's a little graph modeling to help you prep for the final exam. P3, your heaps assignment, is due on Thursday. The TAs, when we had our meeting on Monday, told me that office hours was suspiciously quiet. So I hope you have all started, at least by now, and that it's just going really well, and you don't need the TA help, right? That's what I'm going to assume. Yeah, cool. Yay. So P3 is due Thursday. As a reminder, that means P4 will come out on Thursday, and that's your last programming assignment because it's week 7. Amazing. But best for last, P4 is absolutely the most complex of the programming assignments that we have given you so far. I say this a little bit to put the fear in you so that you start early. So right now it's going to go out. It will be due the last week of the quarter. It has 2 pretty hefty components. One component will be implementing Dijkstra's. Another will be implementing Kruskal's, but it has like a cool GUI where you can see the mazes being built and then like solving the mazes, which is a very common graph technique. So hopefully it's like a fun thing you can talk to all of your other nerdy friends about, or a fun thing you could put on your resume because it's like a hefty multi-week assignment. That was the intention behind it. Please do get started on that early. That one will not be fun to do in a 1-week situation. Yes?
So we have already covered all the class content we need for P4?
So after today, well, okay, after Friday, you will have absolutely everything you need for P4. But like I said, P4 includes Dijkstra's. So at this moment in time, like on Thursday, you could definitely get started on Dijkstra's and probably even on some of the disjoint set stuff. But Friday, I'm going to finish up the little bit of the disjoint set implementation for you. So then you'll be totally set. And technically, Friday is our last day of the graphs unit. From here on out, it's just a bunch of important topics in computer science, that kind of thing. Of course, my regular reminder that your midterm resubmissions are due Friday, and I can't take late submissions on this. So can you use your late days on the midterm resubmission? No, thank you. I'm sorry. I know this is very high school teacher of me, but no, you can't do that. I know it's mostly just because, like, I know it's wild to be waiting for your final midterm score in week 8 of the quarter. We just want to get this grading done. But, I don't know. Trying to make sure that resub happens. Cool. Any administrative questions at this time? Cool. Okay. Great. Let's talk about our last data structure. I know, it's almost sad. Okay. So Monday we talked about Kruskal's, like we just did, and I gave you this pseudocode in order to accomplish it. So, we kind of like initialize every vertex as its own little island. We sort all of the edges by weight. We loop over each edge. We check what blob each of the vertices on either side of a given edge we're considering is in. So we pull out, let's say in the first iteration of this loop, the smallest possible edge weight, and we look at the two vertices on either end of it, and we ask, are they already connected by the MST? And if they are not, then we add this to our final result, and we union those two things together. The amoeba consumes the other one. I don't know. In the island hopper, we've built a bridge, whatever you want to call it. But this is very pseudocodey. I think it's probably unclear how you would actually code this up. It turns out, in order to code this up, you need a new data structure. So, welcome to the disjoint set. All of those kind of question marks. Now what we're looking for here is the disjoint set is going to be the data structure that manages this idea of like initializing all the vertices to be a single element, and then checking if the vertices are on either side are in the same group, and if they're not unioning together. So all of those things that I've highlighted in the pseudocode, see how I turned them from like English sentences to real code? I'm not going to explain how to actually use this and build this, but that's the part of the code that you're going to use the disjoint sets in. Again, I give you the pseudocode mostly so that when you're doing P4, you can kind of just go line by line, translate it into executable code. So, the disjoint set. What is a disjoint set? So disjoint set is not a unique concept to computer science. It also exists in mathematics. So hopefully we're pretty comfortable with the idea of a set at this point, a set being an unordered collection of unique items. A disjoint set is a set of sets. Yeah, I know, meta. The disjoint part means that there must be unique values across all of the sets. So we have a set of sets, and for every individual entry in each of those sets, all of them must be unique. Great. This is, so if you want a kind of a visual, here is what we might have referred to as a set before. Maybe it's a tree set or a hash set, however you want to do it in Java, right? Then we have a second tree set, and then we have this gray thing that holds the multiple sets together. That's the disjoint set. So it's a set of sets. You can read that because I wrote it in a paragraph form, apparently. Okay, how do we actually create this thing? So let's talk about the set ADT, the disjoint set ADT. What we're going to need to do is we need some sort of collection of items. We need to be able to create a new set within the disjoint set. And we're going to only allow you to create new sets with a single member, which for Kruskal's makes sense because we kind of start off with sets of just one vertex by themselves. So we need a way to be able to create a set with one item in it. That's that step in Kruskal's where you go in and you make, each thing its own independent member. Then you need to be able to add items into a given set within the disjoint set. You need to be able to remove, check the size, all that good stuff. There we go. There's some more visuals. The things that are different between the disjoint set and the set is we need to be able to find which of these sets within the disjoint set that any given item belongs to. So I kind of mentioned vaguely before this idea of representatives. That's like when I'm talking about, okay, here's one blob and here's another blob. How can I quickly tell if a given item or two given items are in the same blob, what I'm going to do is I'm going to elect a representative of the blob, and I'm going to see if the representatives are the same. That will make a lot more sense when I start getting into this, I promise. And then finally, we need to be able to union. So we need to be able to take two of the inner sets and mash them together so that they become one singular joined set. And that is just straight up a line of code from the cross goals. Let the amoebas merge. I'm probably terrible. I'm sorry. If you're a biology person and that biology makes no sense, I am sorry. I haven't taken biology since high school. Okay. So, find set. This is a little bit of what I'm talking about with the representative. The gray thing is the disjoint set. We have 4 separate internal sets. If I want to call find set of Brian, what it means is look through all of these individual names, and then I see Brian exists over here, which means Brian exists within set number 4. If I want to look for Sherdil, I look through all these things and I find here's Sherdil. Sherdil lives inside set number 2. If I want to find Santino, Santino lives over here. He happens to be in set number 3. Because I can find those representatives, that's what makes the are they in the same set thing very quick, because you just find set of Kevin, which, let's see, Kevin's over here in set 1, and then find set of Eileen. Oh, look, Eileen's also in set 1. So that's how I know that they are together already. If their set representatives were different, they're in different sets. Any questions about this kind of concept, how we're checking if things are already contained together? Cool. Okay, so how does union work? We're just going to, again, this is unordered, right? That is one of the key things about a set. A set is optimized for lookup. It's optimized for just associating things together. Doesn't matter who comes before what. So if I called a union of Kevin and Nishu on this disjoint set, I would see Kevin's over here in set number 1 and Nishu's over here in set number 3. So what's going to happen is I just kind of mash Nishu and Santino together with that existing set, thus eliminating set number 3 and growing set number 1. Okay. Make set. We're going to limit it. We're going to try and make this as simple as possible for our implementation, where making a set, it can take in a singular parameter for one type of item that's contained within your sets. So make set of Elena. Here she is kind of hanging out here. Make set of Anisha. Anisha's just kind of hanging over here. And we can do that at any state, right? You can see this sort of, I've been carrying the state of this disjoint set through. Those are the basics of the ADT. Does anyone have any questions on like how the functionality is supposed to work? Yes, please. Ooh, okay, so is the ID kind of like an index? I'm going to do this very annoying thing, and I'm going to say, for today, no. Ask me again on Friday. Because we're actually going to walk through a few different ways to implement this. Okay. Oh, yeah, an example. Okay, so if I create a new disjoint set, it's like my big outer thing. If I create make set of A, make set of B, they all kind of start as their own little lonely islands. I can find union. There we go. Thank you. This is just, I guess I wrote these animations and decided I still wanted to use them. Perfect. There we go. Yes. Aha, there we go, finally. False. So let's talk now about how you actually make that ADT happen. So that's the ADT. There's a lot of different ways to implement disjoint sets. We're going to start today talking about the tree disjoint set. So the way that we are going to implement this is initially we need a set of tree sets. And we're going to call it the forest, because computer scientists love those kind of corny puns. So the forest is the set of sets. That's like our sort of primary field here. But we have another field here that is a map that maps from the value stored in any given node to its actual location. I'm going to explain that in a little bit more detail. We need two other objects in order to make this happen. We need something called a tree set, and that is going to be a special type of tree where we have nodes that have references that connect them together. It's hierarchical. There's only one overall root. So you can see the tree set, it has one field of overall root, and then it has, like add, remove, and it has this extra method, getRep, that tells me what is that representative of this particular tree set. In the past examples, it was like a number, something like that. And then we also need a separate field or a separate object called setNode. That's going to be where we actually store our data. But then it's got this kind of weird other field. Most tree nodes you would expect to have two children, a left and a right. But this set node has only one connection field, and it's for a parent. So this field here, something you will have to use in P4, this is a way for us to quickly find where in the forest any particular given value is existing. Because what we're going to do is we're going to, make everything as its own independent set, and then we might union some things and stuff. And so it's actually really hard to linearly loop over a collection of trees. It's already kind of annoying to loop over a single tree, especially if it's unordered, right? And so instead of doing a bunch of tree traversals within a bunch of different sets, we're just going to create an extra bit of storage where the key is going to be whatever value you're looking for, and then the value is just like a direct pointer to jump right into the middle of whatever tree it happens to exist in, so you don't have to do any looping. This is actually a pretty common way to implement really complex objects like a disjoint set. And I'm going to be real with you, disjoint sets aren't necessarily the most popular objects out there, but I think it's a really good illustration of object-oriented design and how there's a million different ways to do this. And as you get to more complicated objects, they just become collections of objects. So the two fields in the tree disjoint set is a set of sets and then a hash map that gives you from value to where the node is, so you don't have to do any sort of traversals. Question? Thank you for the clarification. Yes, this is my own tree set. Tree set in Java is kind of implemented like this, but not exactly like this. It's got some more fancy stuff going on. So, coming back to this real weirdness of the set node only having a singular next field, right? Like if in linked lists, the connector field is next, and in trees, the connector fields are usually left and right. This one has a connector field of only parent. So what that means is this is actually an inverted tree, and instead of thinking about starting at the overall root and recursing down from parents to children, instead, we're going to use our hash map to jump into a given node and then follow the parent pointers up to the overall root. So we are traveling through this tree in the complete opposite direction we're used to doing so. Instead of recursing from overall root down, we're going to kind of loop from children up to the overall root. And I think I kind of talked about these things. Yep, that's what I was talking about there. And then part of the reason we're doing that is because the thing that's nice about trees is they always have just one overall root. What's like a built-in representative? So instead of finding some other thing where we label each of the sets with a number or something like that, we are just going to sort of deputize whoever happens to be the overall root. That's the representative for the entire group. It's like, yeah, you could say Destiny's Child, but if you said Beyonce, I know what you mean. She's the representative. Sorry, Kelly. Okay. Any questions so far about these things? Okay, so there's a lot of different objects at play. This is just a way to help you visualize it. So the tree disjoint set, that's the container. The tree sets, in this particular example, there are 4 tree sets stored in the field that exists inside the tree disjoint set named forest. So this forest has 4 tree sets. Within each tree set is some number of set nodes, representing, in this particular case, names of my TAs, possibly from 2021 or something. So here is a set we're going to call Kevin, because Kevin is the overall root, and Kevin has 2 other TAs hanging out with him in that singular tree set, Eileen and Keanu. Questions about how we've got sort of 3 different objects floating around here? Okay. Dangerous. All right. Okay, let's dive into implementing the individual functions of the disjoint set ADT. So make set. I think about my forest as a big open field first, and then I am going to call make set on the values 0 through 5. It's like I've gone out into my empty field and I've planted 6 individual saplings. And then I have my map here, so there, and my map is going to store from some key, which we're going to use 0 to represent the value 0, the reference of where in the forest to find it. So I've got 6 separate tree sets contained within the disjoint set. Inside each tree set is one singular set node. And I have my wonderful map to immediately look up where any individual set node is. What is the worst case runtime of finding where in the forest a given set node is? Any brave soul? This is a hash map, if that makes any difference to your ideas. Yeah, in the back then. O of 1, because it's a hash map. So if I'm like, hey, where in the forest is the set node with the value 4? I would come into my hash map, I would jump to 4, I would say, boom, there it is. That's the reference to it. I don't have to loop over anything. Constant time lookup, which is usually what we're looking for in sets, right? Any questions about make set? Make a new tree set, make a new node. Well, really, make a new set node, put that set node in a new tree set, add it to the forest, update your hash map with a reference of where the heck the thing is that you just made. Okay, now let's talk about find. So you might be like, okay, like I kind of get the tree thing. It's got that one overall root. We've got a built-in representative. That is nice. The other reason that we use trees in this particular case is because trees actually are very flexible. Remember, technically, by definition, a tree is a graph. And we don't care about the order of how these things are associated, right? Like in our crust goals, we don't care how directly connected some vertex is. It's just about whether they're associated together in the same collection at a given time. So we're going to use trees to just stick a bunch of nodes together. And it doesn't really matter which parent any particular node is pointing to, as long as they all point upwards to the same overall root. And this actually ends up becoming pretty simple, I'll say, implementation-wise, because then in order to take something from a different set and mush it into another one, all you got to do is change a pointer. So that's why we're using trees. It gives us a lot of flexibility of moving things around, which is usually what we want out of sort of a node-like structure. So when I ask for find, like let's say I want to find Ken, the first thing I'm going to do is I'm going to come to my node inventory hash map. And I'm going to say, node inventory hash map, get me the pointer to the set node that contains Ken. And I'm going to bloop, bloop, jump right here to this node. And then I'm just going to follow my parent pointers until I get to a node whose parent pointer is null. And in this case, I only have to do one jump. I'm like, Kevin, do you have a parent pointer? Yes, you do. Better follow it. Oh, Joyce, do you have a parent pointer? No. Joyce is the representative for Ken. So if I called find Ken, it would return Joyce. So you start at the node inventory, you jump to what you're looking for, and then you travel upwards. If I was like, find Alex, I would say, hey, hash map, where's Alex? Boom, he's right there. And then I'm going to travel up to Ken, I'm going to travel up to Joyce, and then I would report Joyce is my representative. Yeah?
So does the node inventory not store Ken?
Oh, it does, but this is very impossible to see. I just couldn't fit it on the slide. But thank you. Yes? Questions on how this works? Okay, how do we implement union then? Let's say I want to union Ken and Santino. What I'm going to do is first, I'm going to call find each on Ken and Santino. That's how I know whether or not they're in the same collection. And if they're not in the same collection, then I have their two overall roots, and I just update the parent pointer of one of those overall roots, which we know is null, so I can just add something to it without losing anything to point to the other overall root. So if I'm unioning Ken and Santino, I've got my hash map that's like, find me Ken. I would jump in here, and then I would follow the parent pointers, and I'd be like, oh, Ken's overall root is Joyce. And then I would say, okay, find Santino, and I would jump here, and I would move up, and I'd say, oh, Santino's overall root is Eileen. And then I would just set one of these overall roots, either Joyce or Eileen, to point to the other one. And now we've got one big happy blob where everybody, in this case, I picked points to Eileen. So that's how we're unioning things together. It does not matter where in the tree things are. It just matters that they're all connected in the same family tree. Any questions on that? Yeah.
In the picture right now, there's only like 2 pointers per box. Is that necessary or no?
Thank you. You know what's funny is I looked at this and I thought that same thing to myself. So actually, question annoyingly back to all of you, if every node can have up to one parent, how many children can any parent have? Yeah. Infinite. Because technically the parents don't even know about the existence of their children, like problematic, but that means that, you know, you're going to store one parent pointer. Technically, any parent could have infinite children that know about them. I just only used 2 because I guess I could only fit on the slide or something. That will come in handy as we start to get to the optimizations. Now, you may have asked yourself, but Casey, do I really need to find both of the overall roots? I just need them to stick into one thing, so why don't I just find one of them, one of their overall roots, and since I know that overall root will be null, I should just stick it into the other person, right? Doesn't matter, I'm just making blobs. The order doesn't matter. Well, if you're starting to think about runtime, we were using a hash map so we don't have to iterate, right? That's really great. We started with constant time of find the individual set node. But in order to find the representative, that runtime was dictated by how far up the tree I had to iterate until I got to the overall root. Which means how tall any of these given tree sets are will dictate the runtime. So I'm going to find the overall root of both of the sets, and unlike the previous example, which is, we'll say the basic idea, I'm going to add an optimization where I am going to only add the smaller tree into the larger tree because that is less likely to grow the tree height. Again, returning to our sort of example here, if I, had just found Ken and then pointed Ken directly into Santino, like I had found Joyce was Ken's overall root, and I just plugged her into Santino without even bothering to find out where Santino is, look at how much taller this has now. 1, 2, 3, a height of 4, versus the way I did it previously, that had a height of 3. So I am going to find both of their overall roots, and that way I can make sure that I point directly to the overall root and not the other thing I was just trying to mash it into, because I'm trying to keep the tree short. Now, question back to all of you. What do we think is the least optimized orientation for any of these given tree sets? What's the worst case, worst orientation any of these individual tree sets can take? Yeah, like 5 separate people all did this gesture. Correct. So let's say I had a disjoint set that's these 4 items hanging out here, and I called union of A and B, and I plugged A into B, and then I called union of B and C, and I just was like, oh, well, I'll just, find the overall root of B, and I'll just add it to whatever the heck C is, and then I did the same thing with D. I would get that pesky degenerate tree, which is really just a wonky linked list, because that's the tallest a tree can be, and the height of the tree is going to dictate the runtime, because whenever I need to find something, however many levels up the tree I have to go is going to add to my runtime. So this is the degenerate case. If I had to find A, that's really unfortunate. Yes. So we could theoretically encounter a linear runtime if we have one tree set that's just a linked list, and I call find on something that happens to be at the bottom of that degenerate tree. Yes, great. So how do we avoid the degenerate tree? Now, this is kind of like the hashing situation, where we're going to do things that hedge our bets, or like make it very statistically unlikely that we get a degenerate tree, but it's not like the AVLs or the red blacks or the LLRBs where we're going to force rotate things. We're doing no rotations or anything like that. We're just going to add a lot of little optimizations that try and keep our trees as short as possible. And so one of the optimizations we're going to do is what we are going to call weighted union. And that's just a fancy way of saying, take the smallest tree and stick it into the biggest tree. Because that way, the bigger tree can probably just absorb the smaller tree without its height growing. What does that mean? So, why don't you take a few minutes and practice? Here is a disjoint set. It's got 4 separate tree sets in its one forest. Draw the final results of this disjoint set if you perform a union on 2 and 13, a union on 4 and 12, and then a union on 2 and 8. But make sure that you always add the smaller tree, the one with fewer nodes, into the larger tree, and make the smaller tree's overall root point to the larger tree's overall root. And remember, you can have infinite children. Go ahead, take 3 minutes, chat about it. All right, so I can get you out of here on time. Let's chat about it. So if I called find set of 2, what would it return? Find set of 2. What would it return for me? 2. Yeah, 2 is its own representative. Love that. Love that for 2. Okay, if I called find set of 13, what is it going to return? 7. Yes, absolutely. 7. So, which is the larger tree? 7. So I'm going to just update 2's overall root to point to 7. And which is nice, so now we've eliminated one of the tree sets. We've gone from 4 tree sets down to 3. And 7, now that tree has a weight of 3, but its height didn't grow. Convenient. Okay. If I called find set of 4, what is it going to return? 6. Love that. And if I called find set of 12, what would that return? 8. 6 or 8? Which is the larger tree? 6. So I'm going to just update 8's parent pointer. So now I have this blob. And so you can see here, this is an example where, it doesn't matter how many children at each level, as long as everything eventually kind of points upwards towards 6. So now it's finally time. If I called find set of 2, what does it return? 7. It's changed, right? If I call find set of 8, what does that return? Okay, between 6 and 7, which is the larger tree? Ooh, bold choices. I love that. Be a rebel. So we add 7, and now our forest has been dwindled down to a single tree that is this massive blob, and theoretically at this point in time, we've found the MST and our cross goals is done. Any questions? I technically have 2 minutes, but I know asking you to stop packing up is a losing game. Cool. All right. Perfect. That's exactly what I wanted to get through today. Come back on Friday for how to actually implement this. Thanks so much, team.
Thank you, Theory.
Well, hang on. Let me do the...